Welcome back, everyone, and today we're going to return back to doing armatures. And in today's video we're going to deal with how to calculate the weight of a vertice in relation to the bone it's near. This is something you probably don't even think about doing at all, because normally you're going to do all this in an application and then load in your models. But I want to do a lot of procedurally generated content in the future. So one of the most important things I need, especially if I want to deal with procedural animation and things like that, especially if I want to create the models on the fly, simple models, but I need to calculate the weight that the vertices have in relation to the bone. So this is where we left off, kind of one of the last times we were dealing with armatures, where we hard-coded the points to the bones. We built it in such a simple way to know what the weights are per bone. What we need to do is do this automatically. We need to be able to just say, here's a bunch of vertices, here's the bones, figure it out. So that's what this whole video is about. And on top of that, I rebuilt all of Armature, a skeletal system, into ECS. So it now will work with fungi. So how do you figure it out? I actually sat down and tried to figure out a solution for myself. So this might be the best solution. It might be a brute force solution. There might be better, more intelligent ways of doing it. But I managed to come up with my own solution of how to figure out how much weight that vertice has to a bone. So normally, when I start creating this, I start calling it skeleton and bones. Then I switch it over to armatures and joints, because ideally, what we're really working with code-wise is just joints. They're just little origins of rotation, just points of rotation that you can do. You can move them too. You can change the position, but mostly because they're joints, they're mostly just rotation, just really related to rotation. So I call them joints for that specific reason. To make a joint into a bone, you need to define something else. You need to define a direction and a location. So in this case, my joint is right here at origin, and I give it a direction, which is up. By default, it's an up direction, which we did with our armature system. That's the default, no rotation, whatever type of system. Everything points up. And then a length. So it's how long the bone is, essentially, because we need to know how long the bone is. Because if it's just a joint, all it is just a point of rotation. A bone has a point of rotation plus some kind of distance relation. You know, it has like a position relation. So this is a joint now being morphed into a bone, because like I said, originally we were just dealing with joints. So we had to define what a bone is. So we have a joint, we have a length and a direction, and that defines the bone. So I know the length is 1 unit, and there you go. And here's my vertice. It's over there, just minding its own business. So my solution for this is to project that vertice to that bone. So if the bone is all it is just a line, it's just the definition of a segment or a line, you can use projection. And I'm not going to go too deep into projection, because we did this like a lot when we're dealing with recasting. But the idea of projection is to find the closest point that vertice is to here. So I probably should have. I didn't do this, but I should have. Let's do this. Let's give it a red color. And we want to go from start to point. I just want to visually see a line, so this way I can explain it to you better. Refresh. There you go. There you go. Nice. So you have the origin of the bone or the joint itself in relationships. So we already know what the bone definition is. It's this line. Now we had to determine how far in what direction is this vertice to that joint. And what we need now we need to determine is by using projection, projecting this onto this. So the idea is that when we do a projection using the equation, we will get the position on the line right about here. Let me zoom in a little bit more. It should be right about here. So by projecting this to this divided by this squared will give me this position. And that's called projection. So if we do project point onto line, so we pass in the start of the line, the end of the line, and then the point we want to manipulate. So the equation is this. It's dot A, B, give me the dot product of A and B divided by the dot product of AA. But it's really just A squared, really, because it's A times A. But these have to be vector lengths. So we need the vector length. So we know what AB is. So we know we have the start and end position of A and B. So A is going to be A and B. So it's B minus A. That gives us the vector length of A and B. Now that red line is AP because it's from the origin to the point of vertice. So we take the same origin and we say P minus that origin, that joint position. So that creates our vector length of A and B, AB and AP. So this is A and this is the actual B in this equation. To get the dot product of AB, which is A times A, you can just get AB length squared because it's the same thing as a dot product. I can just do vector dot AB AB and it will create the exact same value as this. So these two are equal. Length squared. But this one I actually do the dot product of AB and AP. So AB, AP, A and B. And then you just divide it. Do the division, and that gives you T. That gives you the time from origin that vertice hits. So once you have time, you can then scale it by AB, because AB is that length, that vector length, and then add the origin to it, and that will actually give you the position. So if I were going to write this, it would be it'd be it'll be AB length times T plus A. So that's the equation, really. Or joint position. There you go. That probably makes more sense. Why not? Just say bone length. It makes more sense, I guess, this way in this context. So bone length times time plus joint position. That will give you the position and there you go. So we're projecting that, so we know what the closest point is. Now we don't necessarily need to know this point. I'm just showing you in reference to it. We only need this point for stage 2, but to start with, the first thing we need to do is make sure that this point exists somewhere on this line. So if this point were to say be there, refresh. As you can see, it's no longer there. It's not connected to the line. Now the thing is that what that t value is 1.2. So the first thing we can always check to see is once we project it, is the t between 0 and 1? Technically, is it between? Yeah, well, there's a little caveat to that. But let's say for now, as long as it's between 0 and 1, that means that vertice can be connected to that bone. So if at this point it's not connected because it's a value greater than 1, so we know it's nowhere near within that range of that bone. So that vertice cannot be associated to that bone. And actually, its t value is also its weight. So let me go back and undo, say 0.2. Refresh. So now it's here, right? And its t value is 0.2. This can actually be its weight value, but not really. It has to be the inverse of this value. So you have to say 1 minus 0.2, which is 0.8. That means the weight of this vertice is 0.8. If this was actually down right at the joint, that means its weight would be 1. Because at that point, it would be at origin, the value would be 0. So 1 minus 0 is 1. That creates the value 1. So 1 means you have absolute weight. That joint has an absolute influence on the rotation of this vertice. Okay? And the further up you go, you do the inverse and you less weight. Now, like I said, there's a certain caveat when you're dealing with bones. Because let's say if you have another bone after this, you have to share the weight. So this t value can be the weight of the next bone that this vertice. So the next bone has a little bit of relations by 0.2. But to this bone, it has 0.8. So this bone is 0.8 and the next bone is 0.2. So they have to share the weight if there is a second bone after the current bone you're working on. So if you're calculating the vertices for this bone, you have to know if there's a bone after this, because that means you have to share it. And if there is, like I said, the caveat is, if there is another bone, then the value that you're comparing has to be less than 0. It has to be between 0 and like 0.999999. Because once you hit 1, that vertice then has absolute influence by the next joint. So we're going to work through that, but that's, like I said, the little caveat when we're dealing with bones. And the other thing we need to do is to calculate the distance. Because let's say if I have 2 legs, right? Let's say I have another bone here that's 2 legs. I don't want this vertice to have any weight on this bone, even though I might have another bone right here. Because that means the weight on this, if I had another bone here, that really belongs to that bone. So the next thing you have to do, once you figure it out, it's even within the range of the bone, between the start and ending of the bone, how far away from it is it. So once you have that range and you know you're within it, then you calculate this point, and then you calculate the length of this point. And then at that point, you just pick an arbitrary range or distance. So let's say the distance has to be 0.2. If it's 0.2, well, this is too far. This is a 1. So this means this bone doesn't influence this at all, because it's extended the maximum range of influence. So you kind of have to define the range of influence a bone has on top of that. Wow, that's a lot of talking. So with that in mind, I can then do this. So, like I said, I rebuilt Armature for ECS. So this is what it looks like to create bones and armatures and whatnot again. So I create my armature. I'll make an entity first. Then I initialize that entity to use armature, the armature component. I get the armature component, and then I can use the armature object again. Use these static functions and pass in the data. And I want to create all these bones. And then I pass in, what parent they're related to, because we need bones to be connected to parents. And the only difference in this version of Armature of the armature is that I can actually define the length of a bone for the joint. So this way we have that range. And the beautiful thing about this thing is that I don't have. Before we had to reposition every bone or every joint in relations to its parent. This is done automatically for you. So if I know this is a length of 6. When I create the next bone, it's this position is at the end of wherever this is. So it just keeps tacking on. And then we sort the joints. That's a new function. And then we bind post. A lot of the same thing. And then we have the Armature Preview, which uses the exact same entity, which creates another component. And I'm using the stick preview and then using the preview material or shader. And then we're just going to create some random points, and we're going to apply weight to it. So let's see what it looks like. Refresh. There we go. So as you can see now, you have 3 bones. Maybe it's a little hard to tell. The red is the start, green is the end of the bone. Like how I always had the armature system built up. And you'll see all these random points, and we're calculating to see where everything else. Anything that's connected, the gray line, is what bone it's connected to. And as you can see, this vertex has no connection because it's outside a specific range. So yeah, this probably just by 1 lens. Probably a long range, it's like a range of 1. And yeah, it's like I said, if you want to take that basic concept and just start applying it as an array, you can then just do that. So we'll look at the code, but it's basically doing that idea, but in a loop. So I'm going to loop all the vertices, and for every vertex, I'm going to compare it to every bone. The only thing I'm going to do is that I have something called get bone info. And get bone info prepares all the bone information that I need. So this way I'm not recalculating it every time. So this way I know the start and end position. I know its length. I know its length squared. I know its length squared inverse. And I know the index of the next bone. If the index equals -1, that means there's no next bone. So I'm using that to tell me, just as a note. And then I have a function here that finds the next joint. So all it does is searches. If it finds more than 1 joint, it does -1. Because if you have more than 1 joint, it's kind of hard. I don't want to add that complexity yet. Where if there's multiple, if I need a vertex to connect to its current point, but then more joints afterwards, I just want to do a single joint. For now, so as long as there's a single, as long as there's only 1 bone ahead, the weight gets shared. So this way you can do legs, you can do arms, you can do the torso because you have like 3 bones for the spine. You could do tentacles. Later on, I really want to do spider legs, so you have like 4 legs, and I want to do an armature, like procedure generated animations. Like that, so and like IK and I'm going ahead of myself. So yeah, I just want to pre-calculate all the bone information, so this way I don't have to recalculate over again. So because let's say there's like 10,000 vertices, I need to have all this information of every bone because the armature for the most part, does not treat everything as bone. It treats everything as joints because that's the only time that it really matters. So, like I said, there's only a little bit of data of length to help define the overall bone, and this is all the information that helps me define the bone. So, like I said, I just pre-calculate all the bone information, and it's all the stuff that I do here. So it's a rehash of this in just a more complicated, in a loopy way. Yeah, and I have comments to explain it. So this way, I'm just getting all the bone information. So I end up looping all the vertices, and then I take that vertice that I currently working, and then just loop all the bones and try to find out, do the projection. Is the value between less than, if the value is less than 0 or greater than 1, or if it is 1, but there's no bone. So if the value equals 1, but there's no next bone, I still want to count it. So essentially, so that's one of the conditions. So here's the first condition of the vertice with the bones. Make sure you're within the range, and that's it. Like I said, I'm just checking the range. If you're within that projection range of the bone. The next thing I just check its length, and I use length squared because I pass in the range, and then I say range times range and length. Since I'm doing a lot of looping, I want to make this faster, so I don't want to use square roots. So I'm not going to use exact lengths. I'm using length squared because I automatically get the length squared anyway. And like I said, I pre-calculated certain things. So I just have to, here's some like simple equations, but that's like at this point I'm just checking to see if it's within that range. If it's not within that range, I'm just going to continue. It's not. It's as long as if it's greater than the max length, exit out. And then here I just end up calculating the actual weight. So if there is no next bone, the weight is 0. If there is a next bone, this bone gets 1 minus t, and the next bone gets t, that projection value that we get. And then we use the init joints for the geo object, for the vertex object from the geo stuff, geometry class. So we initialize the joint. We say the current index of the bone we're kind of accessing, and then the next bone. And if we have 0, we have to have 0. We need, just to make things work, we still need to identify. So, but if we have the weight of 0, that's why I have the next weight is 0. It all cancels out anything in the shader code. And then we just add in the weight. So we have which bones we have access to and which weight. And our armature allows up to 4 bone influences per vertex. You probably won't need more than 3. I think 4 is the maximum because we're using a vec4. So I have all that. So you can have up to 4 bones influencing one vertex. And I think that's kind of like a standard thing anyway. And that's it. And this is what ends up updating the joint indexes and the joint weights. And that's it. And like I said, I have it visually showing here that these 4 are associated to which bones and whatnot. So every vertex is compared to all 3 bones. So this one, check that bone, that bone, that bone, and the only bone that has influence is this one, because it's the only one that's closest and it's within this huge range, like this circular radius of it. So the range is is actually just a radius. In this function also takes into account it's this bone thing. I probably forgot to mention. I show lines. I show that the lines are straight, but over here I'm taking rotation into consideration. So I take the origin and rotation and figuring out where the joint, because when you create your bind pose, you might actually rotate your things a little bit. So I take consideration the rotation of the bone when I'm assigning. So this way I get this. The joint is a starting point, and then I rotate the position of where the end point of the bone is. So I just forgot to mention that. That's one of the important things I'm doing here is like everything I'm showing you is kind of straight up and down, but when you're doing an actual armature or any kind of skeleton, you're going to have a predefined pose as a starting point. So, and then you put your normally you do your vertices, then you put your bones where the vertices are, and that's you have to take rotation into consideration when you define your bone. So we know what the length is, we just figure out the end position, and that's all that code here is for, just figuring out the end position of the bone. And it takes care of the world position as well, because the position, it's all world space. It's world space beginning and end of the bone. And that is everything you need to do to calculate the weight or define what bone the vertex connects to. So yeah, blah blah blah. And if I go to ECS weights, there you go. Now this object, it looks the same. The only difference is instead of showing the points, I do a line. I do a line strip. So if I go to here, the weights is the new one. So yeah, line strip. But if I want, like how the original one was with points, I can just do this. Refresh. There it is. But this is the one that uses the new functionality. So I build my shape just like before. I just have little definitions. And then I say the object weight, geo weight. So I pass in the geo, I'll pass in the arm, and then end up calculating everything for me. And then from there, I can then just create everything. Load. The only thing I haven't really figured out yet is how to handle drawing armature. So every armature has a draw function. So this way it can set the joints. So I need to fix that. But like I said, I haven't come up with a solution yet. So everything's kind of bare bones. Build shape is easy. Like I said, this is like a rehash from the original armature function. And I have a function for animating. And now in the original one, just quickly, this is a hard-coded. So I kind of just do a bunch of math that has kind of basically this it uses a pattern to calculate it. But if I wanted to add in more vertices, I would have to redo all this math. And if I want to move things around, I would have to redo all this math. If I start adding angles, it just becomes super complicated. I just wouldn't be able to hard code it. So that's why I built that function to do it. So this way, let's see. Where is it that I'm trying to figure out? Geo. Oh, build shape. Oh, that's right, I'm using the wrong one. All right, here's the one that we're really going with. So I have build shape. Build shape is different because I have two extra parameters. Here I'm saying I want 6 elements, and I want them 0.3 away. That means if I want to, I can say I want 12 instances of the shape, but I want them 1 point distance 5 away. Because I want half of 3, because I still want everything within the range of my current bones. Click refresh. And there you go. I have more. Maybe you can't tell, but I can probably make it more denser. I don't know. Let me just do 0.5. Let's see what that looks like. Even like I change the size, you can see those other bones don't have influence because it's automatically taking the influence of the first bone and the next bone that it connects to. So if I want to, I can probably do 32 or 34. Let's try 34. Refresh. And there you go. Now you might just see a little oddity because the last bone has complete influence over it, and you kind of need that because if I don't add that 100% thing, all these points get left behind. It looks really nasty. So it's not perfect. Like I said, this is like a brute force version of this, but it does it if I need to prototype everything and test it. And like I said, I can further down, just kind of fix it up and make it a little bit better. Like I said, but yeah, it's. I probably need to figure out a better way to define the influence between bones. That's about it. Like there's that, it's near the origin that the influence is a little off. But it's like I said, this is it gets you there because there's not really anything about this, because that's why I kind of just went and tried to figure out a solution on my own. I think that's it for prototyping. You know, like the only thing I can really show you is I did a bunch of different animations by modifying the bones. This is kind of more of mechanical, like a kind of broken mechanical movement, which is just using an easing function and a triangle wave. Instead of a sine wave, I use a triangle wave, throw that into a bouncing easing function, and we're good to go. You got this if you want. Refresh. I think that's just a sine wave, and that's just how the motion of a sine wave is. See, I didn't do it this densely. That's why I didn't notice this problem before. See, now cause I did it like this, so I did most of my testing this way. So I didn't notice that little problem. But yeah, here you go. It's kind of like a spring. I kind of like that you can take a spring, you're bending it. So, but that's the overall idea of finding which vertex that connects to which bone. Now you can kind of play with the weights, how to distribute the weights. And the way you distribute the weights can be maybe slightly different algorithm than mine's, but maybe a better algorithm. Like I said, this is kind of like a brute force way of doing it, because I couldn't. There's not really a lot of information related to this, and that's why I kind of said this probably something most people don't care about. But this is kind of like I said. I want to start doing procedural animation. Instead of animating things with the tool and loading in the animations, I want to procedurally do it. I want to do, the next video is probably going to be a walk cycle, completely in code. It just by moving the bones around using forward kinematics. So that's kind of why I wanted to do this. So this way I can, if I want to put a mesh around the skeleton, I can do that and have things move around. So I'm gonna start dealing with forward kinematics and learn how to do animations and really make videos related to that, and then move over to inverse kinematics, so that we can do other types of animations. Like I really would love to make a skeleton robot, a spider robot, and have it walk around dynamically. Like no predefined animation. It's just the bones move in a walking motion, and if for some reason it needs to turn a different direction, the bones will just start acting in a different way. And ideally with inverse kinematics, like let's say if he's if it's terrain, like bumpy terrain, I can actually have the feet touch exactly where it's on the floor, and so it's not like floating in air if it's in weird bumpy terrain. So yeah, so hopefully we're going to build spider robots in the future. So that's kind of my goal with all this inverse kinematics and forward kinematics. So, but yeah, well, like I said, here we go. Armature system is all rebuilt. Everything's working again, and ready to go. So I guess I'll see you in the next video, which will be starting to deal with forward kinematics and building a walk cycle with our armature. See you guys in the next video.